What is the use of the yield keyword in Python? And what does it do? For example, I'm trying to understand this code 1. And this is the caller. What happens when the method _get_child_candidates is called? Is a list returned? A single element? Is it called again? When will subsequent calls stop? 1. This piece of code was written by Jochen Schultz, who made a great Python library for metric spaces. This is the link to the complete source. Module MISpace. To understand what yield does, you must understand what generators are. And before you can understand generators, you must understand iterables. Iterables. When you create a list, you can read its items one by one. Reading its items one by one is called iteration. My list is an iterable. When you use a list comprehension, you create a list. And so an iterable. Everything you can use for in on is an iterable. Lists, strings, files. These iterables are handy because you can read them as much as you wish. But you store all the values in memory, and this is not always what you want when you have a lot of values. Generators. Generators are iterators. A kind of iterable. You can only iterate over once. Generators do not store all the values in memory. They generate the values on the fly. It is just the same except you used instead of. But you cannot perform for I in my generator a second time, since generators can only be used once. They calculate 0. Then forget about it and calculate 1. And end calculating 4. 1 by 1. Yield. Yield is a keyword that is used like return. Except the function will return a generator. Here it's a useless example. But it's handy when you know your function will return a huge set of values that you will only need to read once. To master yield, you must understand that when you call the function, the code you have written in the function body does not run. The function only returns the generator object. This is a bit tricky. Then, your code will continue from where it left off each time for use as the generator. Now the hard part. The first time the for calls the generator object created from your function, it will run the code in your function from the beginning until it hits yield. Then it'll return the first value of the loop. Then, each subsequent call will run another iteration of the loop you have written in the function and return the next value. This will continue until the generator is considered empty, which happens when the function runs without hitting yield. That can be because the loop has come to an end, or because you no longer satisfy an if/else. Your code explained. Generator. Caller. This code contains several smart parts. The loop iterates on a list, but the list expands while the loop is being iterated. It's a concise way to go through all these nested data, even if it's a bit dangerous since you can end up with an infinite loop. In this case, candidates.extend node_get_child_candidate distance min_dist max_dist exhaust all the values of the generator, but while keeps creating new generator objects which will produce different values from the previous ones since it's not applied on the same node. The extend method is a list object method that expects an iterable and adds its values to the list. Usually we pass a list to it. But in your code, it gets a generator. Which is good because you don't need to read the values twice. You may have a lot of children and you don't want them all stored in memory. And it works because Python does not care if the argument of a method is a list or not. Python expects iterables, so it will work with strings, lists, tuples, and generators. This is called duck typing and is one of the reasons why Python is so cool. But this is another story. For another question, you can stop here, or read a little bit to see an advanced use of a generator. Controlling a generator exhaustion. Note. For Python 3. Use sprint corner underscore street underscore ATM underscore next underscore or print next corner underscore street underscore ATM. It can be useful for various things like controlling access to a resource. Itertools. Your best friend. The Itertools module contains special functions to manipulate iterables. Ever wish to duplicate a generator? Chain two generators? Group values in a nested list with a one-liner? Map/zip without creating another list? Then just import Itertools. An example? Let's see the possible orders of arrival for a 4-horse race. Understanding the inner mechanisms of iteration. Iteration is a process implying iterables implementing the iter_iter___ method and iterators implementing the __next___ method. Iterables are any objects you can get an iterator from. Iterators are objects that let you iterate on iterables. There is more about it in this article about how for loops work. Shortcut to understanding yield. When you see a function with yield statements, apply this easy trick to understand what will happen. Insert a line result equals at the start of the function. Replace each yield x pair with result.appendix pair. Insert a line return result at the bottom of the function. Yay! No more yield statements. Read and figure out code. Compare function to the original definition. This trick may give you an idea of the logic behind the function. But what actually happens with yield is significantly different than what happens in the list-based approach. In many cases, the yield approach will be a lot more memory efficient and faster too. In other cases, this trick will get you stuck in an infinite loop, even though the original function works just fine. Read on to learn more. Don't confuse your iterables, iterators, and generators. First, the iterator protocol. When you write, Python performs the following two steps. Gets an iterator for mylist. Call itermylist - this returns an object with the next method or __next _ in Python 3. This is the step most people forget to tell you about. Uses the iterator to loop over items. Keep calling the next method on the iterator returned from step 1. The return value from next is assigned to x and the loop body is executed. If an exception stop iteration is raised from within next, it means there are no more values in the iterator and the loop is exited. The truth is Python performs the above two steps anytime it wants to loop over the contents of an object. So it could be a for loop. But it could also be code like otherlist.extend_mylist where otherlist is a Python list. Here mylist is an iterable because it implements the iterator protocol. In a user-defined class, you can implement the __iter__ method to make instances of your class iterable. This method should return an iterator. An iterator is an object with a next method. It is possible to implement both __iter__ and next on the same class, and have __iter__ return self. This will work for simple cases, but not when you want two iterators looping over the same object at the same time. So that's the iterator protocol. Many objects implement this protocol. Built-in lists, dictionaries, tuples, sets, files, user-defined classes that implement __iter__ generators. Note that a for loop doesn't know what kind of object it's dealing with. It just follows the iterator protocol, and is happy to get item after item as it calls next. Built-in lists return their items one by one. Dictionaries return the keys one by one. Files return the lines one by one, etc. And generators return. Well, that's where yield comes in. Instead of yield statements, if you had 3 return statements in F123, only the first would get executed, and the function would exit. but f123 is no ordinary function. When f123 is called, it does not return any of the values in the yield statements. It returns a generator object. Also, the function does not really exit. It goes into a suspended state. When the for loop tries to loop over the generator object, the function resumes from its suspended state at the very next line after the yield it previously returned from. Executes the next line of code. In this case, a yield statement, and returns that as the next item. This happens until the function exits, at which point the generator raises stop iteration, and the loop exits. So the generator object is sort of like an adapter. At one end it exhibits the iterator protocol by exposing __iter___ and next methods to keep the for loop happy. At the other end, however, it runs the function just enough to get the next value out of it, and puts it back in suspended mode. Why use generators? Usually, you can write code that doesn't use generators but implements the same logic. One option is to use the temporary list trick I mentioned before. That will not work in all cases. For e.g., if you have infinite loops, or it may make inefficient use of memory when you have a really long list. The other approach is to implement a new iterable class something jitter that keeps the state in instance members and performs the next logical step in its next or ___ next _ in Python 3 method. Depending on the logic, the code inside the next method may end up looking very complex and be prone to bugs. Here generators provide a clean and easy solution. Think of it this way. An iterator is just a fancy sounding term for an object that has a next method. So a yield add function ends up being something like this. Original version. This is basically what the Python interpreter does with the above code. For more insight as to what's happening behind the scenes, the for loop can be rewritten to this. Does that make more sense or just confuse you more? I should note that this is an oversimplification for illustrative purposes. The yield keyword is reduced to two simple facts. If the compiler detects the yield keyword anywhere inside a function, that function no longer returns via the return statement. Instead, it immediately returns a lazy pending list object called a generator. A generator is iterable. What is an iterable? It's anything like a list or set or range or dict view, with a built-in protocol for visiting each element in a certain order. In a nutshell, a generator is a lazy, incrementally pending list. And yield statements allow you to use function notation to program the list values. The generator should incrementally spit out. Example. Let's define a function makeRange that's just like Python's range. Calling makeRange returns a generator. To force the generator to immediately return its pending values, you can pass it into list just like you could any iterable. Comparing example to just returning a list. The above example can be thought of as merely creating a list which you append to and return. There is one major difference, though. See the last section. How you might use generators. An iterable is the last part of a list comprehension. And all generators are iterable. So they're often used like so. To get a better feel for generators, you can play around with the Itertools module. Be sure to use chain.from_iterable rather than chain when warranted. For example, you might even use generators to implement infinitely long lazy lists like Itertools.count. You could implement your own def enumerate iterable, zip count iterable, or alternatively do so with the yield keyword in a while loop. Please note, generators can actually be used for many more things, such as implementing coroutines, or non-deterministic programming or other elegant things. However, the lazy lists viewpoint I present here is the most common use you will find. Behind the scenes, this is how the Python iteration protocol works. That is, What is going on when you do list make range 5? This is what I described earlier as a lazy incremental list. The built-in function next just calls the objects.next function, which is a part of the iteration protocol and is found on all iterators. You can manually use the next function and other parts of the iteration protocol to implement fancy things, usually at the expense of readability. So try to avoid doing that. Minutiae. Normally, most people would not care about the following distinctions and probably want to stop reading here. In Python speak, an iterable is any object which understands the concept of a for loop like a list 1, 2, 3. And an iterator is a specific instance of the requested for loop like 1, 2, 3. iter__. A generator is exactly the same as any iterator, except for the way it was written with function syntax. When you request an iterator from a list, it creates a new iterator. However, when you request an iterator from an iterator, which you would rarely do, it just gives you a copy of itself. Thus, in the unlikely event that you are failing to do something like this, then remember that a generator is an iterator. That is, it is one-time use. If you want to reuse it, you should call myRange again. If you need to use the result twice, convert the result to a list and store it in a variable x equals list myRange 5. Those who absolutely need to clone a generator, for example, who are doing terrifyingly hackish metaprogramming, can use Itertools.t if absolutely necessary. Since the copyable iterator Python PEP standards proposal has been deferred, what does the yield keyword do in Python? Answer outline/summary. A function with yield, when called, returns a generator. Generators are iterators because they implement the iterator protocol, so you can iterate over them. A generator can also be sent information, making it conceptually a coroutine. In Python 3, you can delegate from one generator to another in both directions with yield from. Appendix critiques a couple of answers, including the top one, and discusses the use of return in a generator. Generators. Yield is only legal inside of a function definition, and the inclusion of yield in a function definition makes it return a generator. The idea for generators comes from other languages, see footnote 1, with varying implementations. In Python's generators, the execution of the code is frozen at the point of the yield. When the generator is called, methods are discussed below. Execution resumes and then freezes at the next yield. Yield provides an easy way of implementing the iterator protocol, defined by the following two methods: ___iter___ and next Python 2 or ___next___ Python 3. Both of those methods make an object an iterator that you could type check with the iterator abstract base class from the collections module. The generator type is a subtype of iterator, and if necessary, we can type check like this. A feature of an iterator is that once exhausted, you can't reuse or reset it. You'll have to make another if you want to use its functionality again, see footnote 2. One can yield data programmatically. For example, the above simple generator is also equivalent to the below, as of Python 3.3 and not available in Python 2. You can use yield from. However, yield from also allows for delegation to subgenerators, which will be explained in the following section on cooperative delegation with sub-coroutines. Coroutines. Yield forms an expression that allows data to be sent into the generator, see footnote 3. Here is an example. Take note of the received variable, which will point to the data that is sent to the generator. First, we must queue up the generator with the built-in function. Next, it will Call the appropriate next or underscore underscore next underscore underscore method, depending on the version of Python you are using. And now we can send data into the generator. Sending none is the same as calling next. Cooperative delegation to Sub-Coroutine with yield from. Now, recall that yield from is available in Python 3. This allows us to delegate coroutines to a sub-coroutine. And now we can delegate functionality to a sub-generator and it can be used by a generator just as above. Now simulate adding another 1000 to the account plus the return on the account 60.0. You can read more about the precise semantics of yield from in PEP 380. Other methods. Close and throw. The close method raises generator exit at the point the function execution was frozen. This will also be called by underscore underscore del underscore underscore so you can put any cleanup code where you handle the generator exit. You can also throw an exception which can be handled in the generator or propagated back to the user. Raises. Conclusion. I believe I have covered all aspects of the following question. What does the yield keyword do in Python? It turns out that yield does a lot. I'm sure I could add even more thorough examples to this. If you want more or have some constructive criticism, let me know by commenting below. Appendix. Critique of the top/accepted answer. It is confused on what makes an iterable. Just using a list as an example. See my references above. But in summary, an iterable has an underscore underscore iter underscore underscore method returning an iterator. An iterator provides a .next Python 2 or underscore underscore next underscore underscore Python 3 method, which is implicitly called by for loops until it raises stop iteration. And once it does, it will continue to do so. It then uses a generator expression to describe what a generator is. Since a generator is simply a convenient way to create an iterator, it only confuses the matter. And we still have not yet gotten to the yield part. In controlling a generator exhaustion he calls the .next method, when instead he should use the built-in function next. It would be an appropriate layer of indirection, because his code does not work in Python 3. Itertools. This was not relevant to what yield does at all. No discussion of the methods that yield provides along with the new functionality yield from in Python 3. The top/accepted answer is a very incomplete answer. Critique of answer suggesting yield in a generator expression or comprehension. The grammar currently allows any expression in a list comprehension. Since yield is an expression, it has been touted by some as interesting to use it in comprehensions or generator expression, in spite of citing no particularly good use case. The CPython core developers are discussing deprecating its allowance. Here's a relevant post from the mailing list. On January 30, 2017 at 19:05. Brett Cannon wrote. On Sun. January 29, 2017 at 16:39 Craig Rodriguez wrote. I'm okay with either approach. Leaving things the way they are in Python 3 is no good. IMHO. My vote is it be a syntax error since you're not getting what you expect from the syntax. I'd agree that's a sensible place for us to end up. As any code relying on the current behavior is really too clever to be maintainable. In terms of getting there, we'll likely want syntax warning or deprecation warning in 3.7, Py3k warning in 2.7.x, syntax error in 3.8. Cheers. Nick. Nick Colin Coughlin at gmail.com, Brisbane, Australia. Further, there is an outstanding issue, 10,544, which seems to be pointing in the direction of this never being a good idea. PyPy, a Python implementation written in Python, is already raising syntax warnings. Bottom line. Until the developers of CPython tell us otherwise. Don't put yield in a generator expression or comprehension. The return statement in a generator. In Python 2. In a generator function. The return statement is not allowed to include an expression underscore list. In that context, a bare return indicates that the generator is done and will cause stop iteration to be raised. An expression underscore list is basically any number of expressions separated by commas. Essentially, in Python 2, you can stop the generator with return, but you can't return a value. In Python 3, in a generator function, the return statement indicates that the generator is done and will cause stop iteration to be raised. The returned value, if any, is used as an argument to construct stop iteration and becomes the stop iteration.value attribute. Footnotes. The languages CLU, Sather, and Icon were referenced in the proposal to introduce the concept of generators to Python. The general idea is that a function can maintain internal state and yield intermediate data points on demand by the user. This promised to be superior in performance to other approaches, including Python threading, which isn't even available on some systems. This means, for example, that range objects aren't iterators, even though they are iterable, because they can be reused. Like lists, their __iter__ methods return iterator objects. Yield was originally introduced as a statement, meaning that it could only appear at the beginning of a line in a code block. Now yield creates a yield expression. https://docs.python.org/2/reference/simple_grammar-token-yield_stmt. This change was proposed to allow a user to send data into the generator just as one might receive it. To send data, one must be able to assign it to something. And for that, a statement just won't work. Yield is just like return. It returns whatever you tell it to as a generator. The difference is that the next time you call the generator, execution starts from the last call to the yield statement. Unlike return, the stack frame is not cleaned up when a yield occurs. However, control is transferred back to the caller, so its state will resume the next time the function is called. In the case of your code, the function get_child_candidates is acting like an iterator, so that when you extend your list, it adds one element at a time to the new list. List.extend calls an iterator until it's exhausted. In the case of the code sample you posted, it would be much clearer to just return a tuple and append that to the list. There's one extra thing to mention. A function that yields doesn't actually have to terminate. I've written code like this. Then I can use it in other code like this. It really helps simplify some problems and makes some things easier to work with. For those who prefer a minimal working example, meditate on this interactive Python session. TLDR. Instead of this, do this. Whenever you find yourself building a list from scratch, yield each piece instead. This was my first aha moment with yield. Yield is a sugary way to say, build a series of stuff. Same behavior, different behavior. Yield is single pass. You can only iterate through once. When a function has a yield in it, we call it a generator function. And an iterator is what it returns. Those terms are revealing. We lose the convenience of a container, but gain the power of a series that's computed as needed and arbitrarily long. Yield is lazy. It puts off computation. A function with a yield in it doesn't actually execute at all when you call it. It returns an iterator object. that remembers where it left off. Each time you call next on the iterator, this happens in a for loop execution inches forward to the next yield. Return raises stop iteration and ends the series. This is the natural end of a for loop. Yield is versatile. Data doesn't have to be stored all together. It can be made available one at a time. It can be infinite. If you need multiple passes, and the series isn't too long, just call list on it. Brilliant choice of the word yield because both meanings apply. Yield, produce or provide, as in agriculture. Provide the next data in the series. Yield, give way or relinquish, as in political power. Relinquish CPU execution until the iterator advances. Yield gives you a generator. As you can see, in the first case, foo holds the entire list in memory at once. It's not a big deal for a list with 5 elements. But what if you want a list of 5 million? Not only is this a huge memory eater, it also costs a lot of time to build at the time that the function is called. In the second case, var just gives you a generator. A generator is an iterable, which means you can use it in a for loop, etc. But each value can only be accessed once. All the values are also not stored in memory at the same time. The generator object remembers where it was in the looping the last time you called it this way. If you're using an iterable to say count to 50 billion, you don't have to count to 50 billion all at once and store the 50 billion numbers to count through. Again, this is a pretty contrived example. You probably would use Itertools if you really wanted to count to 50 billion. This is the most simple use case of generators. As you said, it can be used to write efficient permutations. Using yield to push things up through the call stack instead of using some sort of stack variable. Generators can also be used for specialized tree traversal, and all manner of other things. It's returning a generator. I'm not particularly familiar with Python, but I believe it's the same kind of thing as C#'s iterator blocks. If you're familiar with those. The key idea is that the compiler/interpreter/whatever does some trickery so that as far as the caller is concerned, they can keep calling next and it will keep returning values, as if the generator method was paused. Now obviously you can't really pause a method, so the compiler builds a state machine for you to remember where you currently are and what the local variables etc. look like. This is much easier than writing an iterator yourself. There is one type of answer that I don't feel has been given yet, among the many great answers that describe how to use generators. Here is the programming language theory answer. The yield statement in Python returns a generator. A generator in Python is a function that returns continuations and specifically a type of coroutine. But continuations represent the more general mechanism to understand what is going on. Continuations in programming languages theory are a much more fundamental kind of computation. But they are not often used, because they are extremely hard to reason about and also very difficult to implement. But the idea of what a continuation is straightforward. It is the state of a computation that has not yet finished. In this state, the current values of variables, the operations that have yet to be performed, and so on, are saved. Then at some point later in the program the continuation can be invoked, such that the program's variables are reset to that state and the operations that were saved are carried out. Continuations, in this more general form, can be implemented in two ways. In the call/cc way, the program stack is literally saved and then when the continuation is invoked, the stack is restored. In continuation passing style CPS, continuations are just normal functions only in languages where functions are first class, which the programmer explicitly manages and passes around to subroutines. In this style, program state is represented by closures and the variables that happen to be encoded in them rather than variables that reside somewhere on the stack. Functions that manage control flow accept continuation as arguments in some variations of CPS. Functions may accept multiple continuations and manipulate control flow by invoking them by simply calling them and returning afterwards. A very simple example of continuation passing style is as follows. In this very simplistic example, the programmer saves the operation of actually writing the file into a continuation, which can potentially be a very complex operation with many details to write out, and then passes that continuation I.E. as a first-class closure to another operator which does some more processing, and then calls it if necessary. I use this design pattern a lot in actual GUI programming, either because it saves me lines of code or, more importantly, to manage control flow after GUI events trigger. The rest of this post will, without loss of generality, conceptualize continuations as CPS, because it is a hell of a lot easier to understand and read. Now let's talk about generators in Python. Generators are a specific subtype of continuation, whereas continuations are able in general to save the state of a computation, i.e., the program's call stack. Generators are only able to save the state of iteration over an iterator. Although this definition is slightly misleading for certain use cases of generators. For instance, this is clearly a reasonable iterable whose behavior is well defined. Each time the generator iterates over it, it returns 4 and does so forever. But it isn't probably the prototypical type of iterable that comes to mind when thinking of iterators, i.e. for x in collection, do underscore somethings. This example illustrates the power of generators. If anything is an iterator, a generator can save the state of its iteration. To reiterate, continuations can save the state of a program stack and generators can save the state of iteration. This means that continuations are a lot powerful than generators. But also that generators are a lot easier. They are easier for the language designer to implement. And they are easier for the programmer to use if you have some time to burn. Try to read and understand this page about continuations and call/cc. But you could easily implement and conceptualize generators as a simple, specific case of continuation passing style. Whenever yield is called, it tells the function to return a continuation. When the function is called again, it starts from wherever it left off. So, in pseudocode, i.e., not pseudocode, but not code, the generator's next method is basically as follows. Where the yield keyword is actually syntactic sugar for the real generator function. Basically something like. Remember that this is just pseudocode and the actual implementation of generators in Python is more complex. But as an exercise to understand what is going on, try to use continuation passing style to implement generator objects without use of the yield keyword. Here is an example in plain language. I will provide a correspondence between high-level human concepts to low-level Python concepts. I want to operate on a sequence of numbers. But I don't want to bother myself with the creation of that sequence. I want only to focus on the operation I want to do. So, I do the following. I call you and tell you that I want a sequence of numbers which is produced in a specific way. And I let you know what the algorithm is. This step corresponds to defining the generator function, i.e., the function containing a yield. Sometime later, I tell you, okay, get ready to tell me the sequence of numbers. This step corresponds to calling the generator function, which returns a generator object. Note that you don't tell me any numbers yet. You just grab your paper and pencil. I ask you, tell me the next number. And you tell me the first number. After that, you wait for me to ask you for the next number. It's your job to remember where you were, what numbers you have already said, and what is the next number. I don't care about the details. This step corresponds to calling .next on the generator object. Repeat previous step until eventually you might come to an end. You don't tell me a number. You just shout. Hold your horses. I'm done. No more numbers. This step corresponds to the generator object ending its job. And raising a stop iteration exception, the generator function does not need to raise the exception. It's raised automatically when the function ends or issues a return. This is what a generator does, a function that contains a yield. It starts executing, pauses whenever it does a yield, and when asked for a .next value it continues from the point it was last. It fits perfectly by design with the iterator protocol of Python, which describes how to sequentially request values. The most famous user of the iterator protocol is the for command in Python. So, whenever you do a, it doesn't matter if sequence is a list, a string, a dictionary or a generator object like described above. The result is the same. You read items off a sequence one by one. Note that defining a function which contains a yield keyword is not the only way to create a generator. It's just the easiest way to create one. For more accurate information, read about iterator types, the yield statement, and generators in the Python documentation. While a lot of answers show why you'd use a yield to create a generator, there are more uses for yield. It's quite easy to make a coroutine, which enables the passing of information between two blocks of code. I won't repeat any of the fine examples that have already been given about using yield to create a generator. To help understand what a yield does in the following code, you can use your finger to trace the cycle through any code that has a yield. Every time your finger hits the yield, you have to wait for a next or a send to be entered. When a next is called, you trace through the code until you hit the yield. The code on the right of the yield is evaluated and returned to the caller, then you wait. When next is called again, you perform another loop through the code. However, you'll note that in a coroutine, yield can also be used with a send, which will send a value from the caller into the yielding function. If a send is given, then yield receives the value sent and spits it out the left-hand side. Then the trace through the code progresses until you hit the yield again, returning the value at the end, as if next was called. For example, there is another yield use and meaning since Python 3.3. From PEP 380. Syntax for delegating to a sub-generator. A syntax is proposed for a generator to delegate part of its operations to another generator. This allows a section of code containing yield to be factored out and placed in another generator. Additionally, the sub-generator is allowed to return with a value, and the value is made available to the delegating generator. The new syntax also opens up some opportunities for optimization when one generator re-yields values produced by another. Moreover, this will introduce since Python 3.5. To avoid coroutines being confused with a regular generator today, yield is used in both. All great answers. However, a bit difficult for newbies. I assume you have learned the return statement. As an analogy, return and yield are twins. Return means return and stop, whereas yield means return but continue. Try to get a number underscore list with return. Run it. See. You get only a single number rather than a list of them. Return never allows you prevail happily. Just implements once and quit. There comes yield. Replace return with yield. Now, you win to get all the numbers. Comparing to return, which runs once and stops. Yield runs times you planed. You can interpret return as return one of them, and yield as return all of them. This is called iterable. One more step, we can rewrite yield statement with return. It's the core about yield. The difference between a list return outputs and the object yield output is you will always get 0, 1, 2 from a list object, but only could retrieve them from the object yield output once. So, it has a new name generator object as displayed in out 11. In conclusion, as a metaphor to grok it, return and yield are twins. List and generator are twins. From a programming viewpoint, the iterators are implemented as thunks. To implement iterators, generators, and thread pools for concurrent execution, etc. As thunks, one uses messages sent to a closure object, which has a dispatcher, and the dispatcher answers to messages. Next is a message sent to a closure, created by the iter call. There are lots of ways to implement this computation. I used mutation, but it is possible to do this kind of computation without mutation, by returning the current value and the next yielder, making it referential transparent. Racket uses a sequence of transformations of the initial program in some intermediary languages. One of such rewriting making the yield operator to be transformed in some language with simpler operators. Here is a demonstration of how yield could be rewritten, which uses the structure of R6Rs. But the semantics is identical to Python's. It's the same model of computation, and only a change in syntax is required to rewrite it using yield of Python. Welcome to Racket v6.5.0.3. Define gen. Lambda L. Define yield. Lambda. If null, L. End. Let vchar L. Set. LCDRL. V. Lambda M. Case M. Yield. Init lambda data. Set. L data. OK. Define stream gen 123. Stream yield. 1. Stream yield. 2. Stream yield. 3. Stream yield. End. Stream init AB. OK. Stream yield. A. Stream yield. B. Stream yield. End. Stream yield. End. Here are some Python examples of how to actually implement generators as if Python did not provide syntactic sugar for them. As a Python generator. Using lexical closures instead of generators. Using object closures instead of generators. Because closures and objects are equivalent. I was going to post read page 19 of Beasley's Python. Essential reference for a quick description of generators. But so many others have posted good descriptions already. Also, note that yield can be used in coroutines as the dual of their use in generator functions. Although it isn't the same use as your code snippet. Yield can be used as an expression in a function. When a caller sends a value to the method using the send method, then the coroutine will execute until the next yield statement is encountered. Generators and coroutines are a cool way to set up data flow type applications. I thought it would be worthwhile knowing about the other use of the yield statement in functions. Here is a simple example. Output. I am not a Python developer, but it looks to me yield holds the position of program flow and the next loop start from yield position. It seems like it is waiting at that position. And just before that, returning a value outside. And next time continues to work. It seems to be an interesting and nice ability. Laughing face. Here is a mental image of what yield does. I like to think of a thread as having a stack even when it's not implemented that way. When a normal function is called, it puts its local variables on the stack, does some computation, then clears the stack and returns. The values of its local variables are never seen again. With a yield function, when its code begins to run, i.e., after the function is called, returning a generator object, whose next method is then invoked. It similarly puts its local variables onto the stack and computes for a while. But then, when it hits the yield statement, before clearing its part of the stack and returning, it takes a snapshot of its local variables and stores them in the generator object. It also writes down the place where it's currently up to in its code, i.e., the particular yield statement. So it's a kind of a frozen function that the generator is hanging onto. When next is called subsequently, it retrieves the function's belongings onto the stack and reanimates it. The function continues to compute from where it left off, oblivious to the fact that it had just spent an eternity in cold storage. Compare the following examples. When we call the second function, it behaves very differently to the first. The yield statement might be unreachable, but if it's present anywhere, it changes the nature of what we're dealing with. Calling yielder function doesn't run its code, but makes a generator out of the code. Maybe it's a good idea to name such things with the yielder prefix for readability. The GI_code and GI_frame fields are where the frozen state is stored. Exploring them with dir, we can confirm that our mental model above is credible. An easy example to understand what it is. Yield. The output is. Like every answer suggests, yield is used for creating a sequence generator. It's used for generating some sequence dynamically. For example, while reading a file line by line on a network, you can use the yield function as follows. You can use it in your code as follows. Execution control transfer gotcha. The execution control will be transferred from getNextLines to the for loop when yield is executed. Thus, every time getNextLines is invoked, execution begins from the point where it was paused last time. Thus, in short, a function with the following code will print. My below answer only speaks from the perspective of using Python generator, not the underlying implementation of generator mechanism, which involves some tricks of stack and heap manipulation. When yield is used instead of a return in a Python function, that function is turned into something special called generator function. That function will return an object of generator type. The yield keyword is a flag to notify the Python compiler to treat such functions specially. Normal functions will terminate once some value is returned from it. But with the help of the compiler, the generator function can be thought of as resumable. That is, the execution context will be restored and the execution will continue from last run until you explicitly call return, which will raise a stop iteration exception, which is also part of the iterator protocol, or reach the end of the function. I found a lot of references about generator, but this one, from the functional programming perspective, is the most digestible. Now I want to talk about the rationale behind generator and the iterator based on my own understanding. I hope this can help you grasp the essential motivation of iterator and generator. Such concept shows up in other languages as well, such as C#. As I understand, when we want to process a bunch of data, we usually first store the data somewhere and then process it one by one. But this naive approach is problematic. If the data volume is huge, it's expensive to store them as a whole beforehand. So instead of storing the data itself directly, why not store some kind of metadata indirectly, i.e. the logic how the data is computed? There are two approaches to wrap such metadata. The OO approach. We wrap the metadata as a class. This is the so-called iterator who implements the iterator protocol, i.e. the __next___, and __iter___ methods. This is also the commonly seen iterator design pattern. The functional approach. We wrap the metadata as a function. This is the so-called generator function. But under the hood, the returned generator object still is a iterator because it also implements the iterator protocol. Either way, an iterator is created, i.e., some object that can give you the data you want. The OO approach may be a bit complex. Anyway, which one to use is up to you. In summary, the yield statement transforms your function into a factory that produces a special object called a generator which wraps around the body of your original function. When the generator is iterated, it executes your function until it reaches the next yield, then suspends execution and evaluates to the value passed to yield. It repeats this process on each iteration until the path of execution exits the function. For instance, simply outputs. The power comes from using the generator with a loop that calculates a sequence. The generator executes the loop, stopping each time to yield the next result of the calculation. In this way it calculates a list on the fly. The benefit being the memory saved for especially large calculations. Say you wanted to create your own range function that produces an iterable range of numbers. You could do it like so. And use it like this. But this is inefficient because you create an array that you only use once. This wastes memory. This code actually loops over that array twice. Luckily Guido and his team were generous enough to develop generators so we could just do this. Now upon each iteration a function on the generator called next executes the function until it either reaches a yield statement in which it stops and yields the value or reaches the end of the function. In this case on the first call, next executes up to the yield statement and yield n. On the next call it will execute the increment statement. Jump back to the while. Evaluate it. And if true, it will stop and yield n again. It will continue that way until the while condition returns false and the generator jumps to the end of the function. Yield is an object. A return in a function will return a single value. If you want a function to return a huge set of values, use yield. More importantly, yield is a barrier. Like barrier in the CUDA language. It will not transfer control until it gets completed. That is, it will run the code in your function from the beginning until it hits yield. Then, it'll return the first value of the loop. Then, every other call will run the loop you have written in the function one more time, returning the next value until there isn't any value to return. Many people use return rather than yield. But in some cases yield can be more efficient and easier to work with. Here is an example which yield is definitely best for. Return in function. Yield in function. Calling functions. Both functions do the same thing. But yield uses 3 lines instead of 5 and has one less variable to worry about. This is the result from the code. As you can see, both functions do the same thing. The only difference is return_dates gives a list and yield_dates gives a generator. A real-life example would be something like reading a file line by line, or if you just want to make a generator. Yield is like a return element for a function. The difference is that the yield element turns a function into a generator. A generator behaves just like a function until something is yielded. The generator stops until it is next called, and continues from exactly the same point as it started. You can get a sequence of all the yielded values in one by calling list generator. The yield keyword simply collects returning results. Think of yield like return plus equals. Here's a simple yield-based approach to compute the Fibonacci series. Explained. When you enter this into your replace and then try and call it, you'll get a mystifying result. This is because the presence of yield signaled to Python that you want to create a generator. That is, an object that generates values on demand. So, how do you generate these values? This can either be done directly by using the built-in function next, or indirectly by feeding it to a construct that consumes values. Using the built-in next function, you directly invoke .next/__next__, forcing the generator to produce a value. Indirectly, if you provide fib to a for loop, a list initializer, a tuple initializer, or anything else that expects an object that generates/produces values. You'll consume the generator until no more values can be produced by it and it returns. Similarly, with a tuple initializer, a generator differs from a function in the sense that it is lazy. It accomplishes this by maintaining its local state and allowing you to resume whenever you need to. When you first invoke fib by calling it, Python compiles the function, encounters the yield keyword and simply returns a generator object back at you. Not very helpful, it seems. When you then request, it generates the first value, directly or indirectly. It executes all statements that it finds, until it encounters a yield. It then yields back the value you supplied to yield and pauses. For an example that better demonstrates this, let's use some print calls replace with print text if on Python 2. Now, enter in the replace. You have a generator object now waiting for a command for it to generate a value. Use next and see what gets printed. The unquoted results are what's printed. The quoted result is what is returned from yield. Call next again now. The generator remembers it was paused at yield value and resumes from there. The next message is printed and the search for the yield statement to pause at it performs.